A warm good morning to my dear students. So today we'll see the case study in particular topic called as Lamis theorem. So let me go first to see what is Lamis theorem. Then we will see how Lamis theorem is applied to various engineering applications. So what is Lamis theorem? Lamis theorem is a mathematical principle that relates the magnitude of forces in a closed triangle theorem system. And it is used to determine the missing force in a system acting on a project, acting on an object. And it's a closed triangle system where the forces acting on the system are coplanar and should be in equilibrium. So Lamis theorem can be applied only in conditions where the forces acting on the system are coplanar and they are in equilibrium. The theorem also assumes that the sides of the triangle are straight and the angles are unchanging. Now, what is the formula that is derived using the Lamis theorem? That is the force 1 divided by the sine of the angle made by the other two forces equal to force 2 divided by the sine of the angle made by the first force and the third force, that is equal to force 3 divided by the sine of the angle made by the remaining the forces 1 and 2. So where F1, F2, F3 are the magnitude of the forces 1, 2 and 3 and A, B, C are the angles opposite to the respective forces. And Lamis theorem has wide applications including in mechanics, in physics and engineering, and it's a very useful tool for solving complex problems involving forces and geometry. Now we'll see what is the practical practice of Lamis theorem. We will consider the application of Lamis theorem in case of a suspension bridge. Let me take the case study of a suspension bridge. Now, in a suspension bridge, the bridge is suspended by means of cables. Now, the entire load on the bridge has to be balanced by the suspension cables. Now, what should be the tension that should be given in the suspension cables so that the bridge is stable? Now, using the Lamis theorem, we can find the tension in the cables of a suspension bridge. So now the two forces acting on the suspension bridge. One is the weight of the bridge and the other one is the load it can bear and height of the tower. So these are the three forces that they are going to act. One is the weight of the bridge, the load it can bear and the height of the tower. Now using these three forces, if the height of the tower and the load it can bear, if they are known, then we can determine the weight of the bridge. Or if you want to calculate the force from each cable to keep the bridge balanced, knowing these two forces, we can find the unknown force. Similarly, Lamis theorem can be used in application of constructions in towers, in buildings. So the same equation can be used. That is, if there are two forces known and the angle between the three forces are known, then the unknown force can be determined by the Lamis theorem. And in physics, it is used as an essential tool for physicists to calculate the balance of forces in case of containers or boxes that are being lifted or moved. It is also used to calculate the tension in the ropes and cables. And Lamis theorem can be also used in robotics to calculate the force required to move a robot arm from one position to another. So it helps the engineers to design a robotic arm that are precise, efficient and safe to use. Now we can see from this particular applications point of view, in case of suspension bridge case study, the Lamis theorem is used in analyzing the tension in the cables of a suspension bridge that has helped to safe and successful construction of the bridge. So the calculation of the tension in the cables allowed for the bridge to be balanced correctly. Second, in case of robotic arm. So understanding the Lamis theorem is essential in design of robotic arm as it ensures that the arms have the optimal balance of forces. This ensures maximum efficiency and precision in the movement of the robotic arm at all times. Going to the physics experiment. In the physics experiment, Lamis theorem was used to calculate the tension in the cable and tension in the rope. And through this calculation, the experiment can be conducted safely and efficiently and effectively with high precision. Similarly, in the construction and engineering issues, Lamis theorem plays a very crucial role in the construction of towers, buildings, and ensuring their stability of these structures. And it helps the architects and engineers to design the structure that are safe, long-standing, and efficient. So some of the possible challenges that can be incurred in the Lamis theorem is that it assumes a closed triangle. So it can be applied only in case of a closed triangle. Thus, it is not always applicable to various real world scenarios. And it is applicable only when the system is in equilibrium and the forces does not change. And in some cases, the Lamis theorem is redundant. So these are some of the possible limitations of Lamis theorem. And if we compare Lamis theorem with other methods, that is vector resolution and method of joints, Lamis theorem is useful when there are only three forces acting on an object, and it is a simple equation to calculate the unknown force in a closed triangle system. Whereas in vector resolution, it uses trigonometry to break down the forces into vector components, and it can be solved using basic algebra. So vector resolution is highly useful when there are multiple forces acting on an object and that are not in the same direction. And similarly, method of joints is actively used in structural analysis and can be more efficient than Lamis theorem in solving complex problem involving forces acting on an object that is not in a closed triangle system. So the method of joints is mostly used in case of structures and frames to analyze the various forces and to determine the unknown forces that is required to keep the structure or joint in a stable condition. So this particular case study focuses on the application of Lamis theorem and the various other methods that are also available to analyze the stability of the structures. Hope you have understood. Thank you.